Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Rabbi shrah li sadri wa yassir li amri wahlul 'uqdatam min lisani yafqahu qawli. Allahumma iftah 'alaina hikmataka wanshur 'alaina min khazaini rahmatika ya arhamar rahimin. Alright, so today we will learn a new chapter about Fourier series. Okay, so basically this is the third chapter. Alright, so first of all, we have to know what is Fourier series. Okay, Fourier series is actually derived from mathematicians Joseph Fourier. Okay, so in Fourier series is used many times in controls, communications subject, and also signal and system. Okay, so basically we will deal with Fourier series and Fourier transform most of the time because you want to see the frequency, spectral, and also the bandwidth of a certain signal. Okay, so Fourier series is used to represent a periodic signal. Okay, so if we want to represent a series, so it must be a periodic. So that means we can put a certain series to that particular signal. Okay, so it will be a periodic signal, and then we will represent it as a infinite sum of a sine wave, or also can be cosine. So a periodic signal is a signal that repeats. Okay, so basically it has a period, so that period repeats the same pattern. Okay, the reason why we use Fourier series is that rather than looking at a time domain, we will see it in another domain, not only in frequency domain but also in a series of sine and cosine, and also exponential form. Alright, so most of the time, like I said, the engineers will be thinking of a signal in terms of what is their frequency and what is their spectrum, and also what is the response for frequency. Alright, so previously we have learned about the system. Okay, so what are the input and output, and now we are concerned about the signal analysis or spectral analysis. Okay, so in this chapter we will show that a periodic signal, so we will learn about more on signal that repeats, periodic, can be represented as the sum of sinusoidal or exponential. Okay, so this is the definition of a Fourier series. Okay, for example, if you want to define a period or a periodic signal, that particular signal must have a period. Okay, so the period usually represented by T naught. Okay, so if we can prove that xt is equivalent to xt plus T naught, that means even it have been shifted to its one period, it will be equivalent. So that signal has a property of a periodic. Okay, the smallest value of T naught, okay, meaning that the one period, okay, the first period satisfies the periodicity condition, so we call it as a fundamental period. So that is the first or the least, the smallest value. Okay, and the 1 over T naught, which is the frequency, is called the fundamental frequency. Okay, so usually it will having the range minus infinity to infinity. So this are the two signal that will represent a periodic signal, because it is also a periodic signal, so it can represent another signal that is periodic. Okay, so this is a function sine. So the period is usually defined as from one peak to peak, because after that it will repeats again, okay, and then it repeats, okay. So it's a periodic signal. So the signal period is 2 pi over omega naught, okay. So this 2 pi means 360 degree, 360 degree, okay, 2 pi. Alright, so just now we have learned that Fourier series will represent as a sinusoidal. So basically it will be made up of a sine and cosine. So A naught is the DC or direct current, or maybe constant we call it. And then there will be signal AN, cos and omega naught t, and BN, okay, must be plus, okay, of the summation, BN sine and omega naught t. Okay, so if we want to prove that this signal is a periodic, okay, so we shows that xt equivalent to xt plus t naught, the fundamental period, okay. So we just ignore the an and bn because this is the amplitude. Alright, so next, if you want to prove it, so let's say we plus this one, plus t naught to the equations. Okay, so we want to check whether it is periodic or not, or prove it. So substitute the t by plus t naught. So I mean it will be shifted to one period. If we shift to one period, is it equivalent to the xt? Okay, so and omega naught t from here, and omega naught t naught, and also this part as well. Then we know that t naught is equivalent to 1 over f naught, which is in this case for cos and sine is 2 pi over omega naught. Okay, so here 2 pi is equivalent to omega naught t naught. Okay, so what happened is we substitute omega naught t naught with 2 pi. Okay, so this is 2 pi and this one also 2 pi. And then we know that 2 pi is equivalent to 1 period. So that means if we plus 2 pi, it will equate or equivalent to cos and omega naught t. So xt plus t naught, just now we have substitute here, is equivalent to xt. Okay, the original signal. Alright, so this one we have explained just now. Okay, so the infinite series of the right hand side, which is the cos and sine, is known as the trigonometric Fourier series. Okay, so this is the name where we have cos and sine. We call it as trigonometric Fourier series. Okay, so this I have explained. So Fourier series, when we talk about series, basically we will have a series of equation. Alright, so the first one is we call as fundamental. Okay, after a constant. Okay, after constant and plus the first one is the fundamental. The second one, the second series is the second harmonic, third harmonic, and so on so forth. Okay, so that means we want to name this one as series. Okay, so we will substitute it from n equivalent to 1 until infinity. Okay, so for example, this is a signal, rectangular signal. Okay, so this signal can be represented by sine and cosine. Okay, but if we just use the first sign, this is n equal to 0 or maybe the first one, but it only contain the first harmonic. Okay, so it can be represented but not as accurate as the original signal, right? So what we do, we add the sine just now, cosine just now, with another signal sine, okay, cos and sine. So now it becomes second harmonic, okay, and then we add another more signal, become the third harmonic. So this signal can almost cover the rectangular or the original signal. And then what happened, we add more harmonics, add more sine and cosine, and then we add more and more. Okay, so what happened at the end, for certain time, it will be almost similar to the signal, original signal. Okay, that is if we add more sine and cosine or more harmonics to this sinusoidal. Okay, so actually this is a simple example, but we can also represent any other signal by sine and cosine with multiple series. Okay, so it will happen. So to show this in a block diagram, so for example, we have this original signal. Okay, assume that this is the TF, fundamental period. Okay, so this is the initial, and then T naught plus the TF. TF is the period. Okay, so when we add average value, so this is the DC. Okay, to start a signal, we put a average value, and then we plus with a cos 2 pi ft. Okay, F, this is fundamental frequency, FF, okay, fundamental frequency. So it becomes something like this, okay, very flat. Okay, and then we plus a sine. So this is what we want to perform the trigonometric. And then cos and sine is added, so it will looks like this one. Okay, and then we add up the second harmonic of the cos, become this one. Okay, that means this one plus cos 2 pi 2 ft. And then also the second harmonic from the sine, and so on and so forth, the third harmonic from cos, and plus again the third harmonic from the sine, and also cos and sine for the fourth harmonic. And at the end, it will looks like the original signal. Okay, so that is Fourier series. That means we put a series of functions of sinusoid to represent a signal. Okay, so actually there is also another signal that can represent this Fourier series. So there are three types of Fourier series. So the first one that we shows just now is called trigonometric Fourier series. The second one is the compact trigonometric. Okay, so for the compact trigonometric, basically we don't have the sign here, so it will put in the compact way. So here also we have C naught, which is equivalent also with A naught. A naught is the, here at the trigonometric is, okay, let's look at this one first. So A naught is actually the average value or the DC. How to find that one is we integrate the signal ft to dt at one period. So we want to see what is the average value. Okay, so an is the coefficient of the cos. Okay, how to find that one? We have to integrate the signal, multiply with the cos n omega naught t dt. So from here we will find the coefficient an, and then we multiply with 2 over t naught. Okay, and also bn. Okay, bn is the coefficient of the sine part of the trigonometric. So we will use the integration of the signal multiplied by sine. Integrate from only one period only, because we want to know the average value. Okay, that is the signal. So if you see here, it's have an n number. So that's mean we can substitute from n equal to 1, okay, here, to n equal to infinity to find the series. So it will be, although here n, but actually it can be a harmonics if we substitute n equivalent to 1 until n equivalent to 2 until infinity, right? So for the compact trigonometric, so it's actually the representation of the trigonometric but a compact way. So C naught, which is the constant, will be equivalent to A naught here, and Cn is the square root of an squared plus bn squared. Okay, so means that we have to find also what is the coefficient of the cos and coefficient of the sine, right? And then we have to know the theta n, the value shifted here, by finding the minus amplitude of the bn divided by the an, and we arctangent that one. So we will know the theta n. So that is the compact trigonometric. Okay, so as we know that actually the cos and sine can also be representable as exponential. So we also can use exponential Fourier series by this equation dn, the coefficient, ej and omega naught t. Okay, so how to find dn is we integrate the signal with minus j and omega naught t dt. Okay, so if we can recall, this is same or looks like the Laplace transform. Alright. Alright, so in order for us to find the Fourier series, the main reason is actually we want to find the spectrum. Okay, that's why we change into frequency. So from the frequency, we can know that that particular signal has a series of frequency. Okay, so that particular series of frequency, we call it as frequency spectra. Okay, so this one we have explained in previous slide. So from the frequency spectra, we can know the amplitude of the spectrum. So this is n number of harmonics, and this is amplitude A. So the first harmonic, what is the amplitude? The second harmonic, third harmonic, fourth, and so on, so forth. And we can also have the phase spectrum by finding the theta here versus the series or n. So at first harmonic, what is the theta, second, third, and so on so forth, right? This spectra shown at the glance the frequency contents of the signal. So as you can see, xt is actually having a certain amplitude spectrum and also phase spectrum from here. So these informations represent the signal xt, the frequency contents of the signal. Alright, so the frequency spectra of a signal constitute the frequency domain representation. So after this, we can just plot the frequency domain of xt. Okay, so this is an example of the frequency domain. So this one is the amplitude. Okay, so for this signal, pulse signal from certain, so this from here to here is the 1 period. Okay, here, this one, it shows here. So when you multiply this one or substitute it with a trigonometric functions, we will get the information of an, okay, an until infinity. Okay, so here it says that the bn is equivalent to 0. So we all only have the an. So plot it from one harmonic, second harmonic, third, fourth, and until the values 0. Okay, if the values has become 0, so that is the end. Okay, it looks like this one is the same, but this one is pulses and this one is square. Okay, for these equations we have t here. Okay, and also the amplitude is different. This is minus, this is a over 2 and this is minus a over 2. Okay, so the equation is going to be different and the frequency domain will be the difference. So this is the spectra. So for the first harmonic, it has a value, but not the second, but the third one have value. So again, the Pn is 0 and A naught also 0. So we have to substitute to the equations just now. These equations, yeah. These equations. Okay. And also we have this one. The rest is the example. Okay. As I said, we can see this Fourier spectrum as a frequency domain representation. So we have the amplitude spectrum, looks like this one for the signal. This is the signal, E minus T divided by 2, and the phase spectrum. So we just substitute the phase. So the phase looks like same, okay, at all time. So this is what you will get from the Fourier series, right? So I will just stop until here. Next class we will see some example how to plot the Fourier series. Okay, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.